Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about competition model. Competition is the way of life, whether any species. So, competition among the species will be about food, about space and any other needs. So, we will be starting with competition between two plant species. So, say this plant is some species 1 and this plant is some species 2. So, in plants they compete for space, compete for nutrition, compete for sunlight and hence this competition model. So, the left hand side which you see is the rate of growth of species 1. It depends on exponential growth, that is A1 times the species. Also, two plants of the same species, they also compete for the same resources, which is water, sunlight, nutrient, space, and hence there is a competition between the plants of the same species and it is called intra-specific competition. Also, there is a competition between the species of two different species and hence this into this. And since this competition will take a toll on the growth of the plant, this is a negative sign, this is also a negative sign. So, basically this represents the growth of the plant, this represents the competition due to same species plant at a rate A2 and this will represent the competition of different species plant and it is called inter-specific competition. The same thing for the species 2, this is the rate at which species 2 grows, follows an exponential growth, an intra-specific competition at a rate beta 2, that is why this negative sign, and an inter-specific competition at a rate B3, again with the negative sign. So, if you replace them by the variables x and y, this will look dx dt is equal to a1 times x minus a2 times x into x. So, it becomes x square because it is of the same species minus a3 into x and the other species we represent by y. So, dy dt is equal to b1 y minus b2 y into y. So, y square minus b3 x into y. So, this is a typical competition model between two species. Now, let us do a little analysis of this. So, we have these two models x and y, they are the number or they can be the densities. Generally, we take them as the densities. So, the very first thing that you have to do is find the equilibrium solution and for that you put this equal to 0 and this equal to 0. So, I take x common, a1 minus a2x minus a3y equal to 0 and this side I take a y common, v1 minus b2y minus b3x equal to 0. So, the solution is from this equation x equal to 0 and a1 minus a2x minus a3y equal to 0. So, when and also from here y equal to 0, b1 minus b2y minus b3x equal to 0. So, when x is equal to 0, if you substitute this value here, you will get y times b1 minus b2y equal to 0. This will give y equal to 0 and y equal to B1 by B2. So, when x is equal to 0, y is also 0. When x is equal to 0, y equal to B1 by B2. So, these two are the equilibrium solutions when x is equal to 0. And please note all these constants A1, A2, A3, they are positive, and so are B1, B2, B3, they are also positive because they generally represents the rate. Similarly, if you have y equal to 0, if I substitute it here, I will get x equal to a1 minus a2x, that is equal to 0, which will give me x equal to 0 and x equal to a1 by a2. So, when y equal to 0, x is also equal to 0, and when y equal to 0, x1 equal to a2 0. So, this is common, this is one equilibrium point, this is one equilibrium point. And finally, if we solve this equation and this equation, that is a1 minus a2x minus a3y equal to 0 and b1 minus b2y minus b3x equal to 0. So, simultaneous equation, linear equation, you can use any method, say method of cross multiplication, and if you solve it, your answer is going to be x is equal to a1 b2 minus a3 b1 divided by a2 b2 minus a3 b3. Similarly, y will be equal to a2 b1 minus a1 b3 minus a2 b2 minus a3 b3. To find this solution, I leave this to you. It's quite simple. You just have to solve this simultaneous equation. So, we have 4 equilibrium points. One is 0, 0, one is a1 by a2 0, one is 0 b1 by b2, and the other is some x star y star, where x star is given by this and y star is given by this. So, once you get the equilibrium solution, you now have to check for stability. So, to check for stability, we have to find Jacobian matrix. So, if I write the equations dx dt equal to x a1 minus a2x minus a3y and dy dt equal to y b1 minus b2y minus b3x. So, the Jacobian matrix, you name this as some fxy and name this as from gxy. So, this is f of x, f of y, g of x and g of y at the point x star y star, and you will get this value to be a1 minus a2 x star minus a3 y star minus a3 x star minus b3 y star. This is b1 minus 2b2 into y star minus b3 into x star. Now, let us take each of the equilibrium points. Say number 1, 0, 0. So, I substitute 0, 0 here and I get the value of a to be a1. This vanishes, this also becomes 0, this also becomes 0, this is b1. If I want to find the eigenvalue, that is, and this will give me minus lambda plus a1, 0, 0, b1 minus lambda, and this gives me lambda equal to a1 and b1. Both are positive because they are the rates. So, real and positive eigenvalues system is unstable. And to be specific, it will be an unstable node, which we have done before. This is some sort of justified because 0, 0 means that both the species becoming 0, which means they go to extinct. So, it is not good for nature that two particular species, whether it is a plant species or whether it is an animal species, they compete against one another and then both of them dies out. So, nature wants coexistence, that both the species must survive, and hence this is quite justified that your 0, 0 is unstable. Let us move to the second one, which is A1 by A2 0. That means the first species is there, but the second species did not survive, goes to extinct. So, if I substitute it, you will get the value of A. So, you have to take this matrix, you have to substitute x star equal to A1 by A2 and y star equal to 0. So, if you do that, you will get minus A1 minus A1 A3 by A2 0 and B1 minus A1 B3 by A2. If you want to find the eigenvalue of this, A minus lambda I equal to 0, which will imply minus A1 minus lambda minus A1 A3 by A2 0 B1 minus A1 B3 by B2 minus lambda. So, if you solve this, it will be minus A1 and B1 minus A1 B3 by A2. It is clear that this is less than 0. Now, your second value, if you want the system to be stable, then this has to be less than 0. So, you get a condition from here that if you want the system where the first species exists, where the second species goes to 0, then B1 minus A1 B3 divided by A2 must be less than 0. So, you can get a condition that B1 must be less than A1 B3 by A2. You can write it in any form. You can write it at A1 A2 is less than A1 B3. What you have to take care is when you are doing the numericals, you have to be sure that if you want a stable system for this particular equilibrium point, this inequality must be satisfied. Our third equilibrium point is 0 B1 by B2. In the similar manner, we get this A, and this is going to be A1 minus A3 B1 by B2. This is 0 minus B1 B3 divided by B2 minus B1. Again, if you want to find the eigenvalue, you will get A1 minus A3 B1 by B2 minus lambda 0 minus B1 B3 by B2 minus B1 minus lambda. And the solution is going to give you lambda equal to minus B1 and A1 minus A3 B1 by B2. So, if you again want this system to be stable, this is clearly less than 0, and if you want the system to be stable, this has to be less than 0, that is A1 must be less than A3 B1 by B2. So, for 0, 0, you find that the system is unstable. For A1 by A2 comma 0, you find the system to be stable provided an inequality holds. Same thing for 0 comma B1 B2, you find that the system is stable if this particular inequality holds. Now, let us go for the non-zero equilibrium point. This will be A1 B2 minus A3 B1 divided by A2 B2 minus A3 B3, A2 B1 minus A1 B3 divided by A2 B2 minus A3 B3. So, this has to be, I mean, a bit laborious. You take that A, you substitute the values x star and y star, and after simplification you will get something like this: A2 times A3 B1 minus A1 B2 divided by A2 B2 minus A3 B3. This is A3 into A3 B1 minus A1 B2. This one is B3 multiplied by A1 B3 minus A2 B1 divided by A2. You could have taken this common, but anyway, A1 B3 minus A2 B1 divided by A2 B2 minus A3 B3. So, once you get this, you have to find the characteristic equation, and which is A minus lambda I, determinant of that is equal to 0. If you want to find the eigenvalues in the form of AIs and BIs, it will be a bit complicated. So, you find the characteristic equation, which will be of the form lambda square plus A2 A1 plus B1 into B2 minus A1 B2 B3 minus B1 A2 A3 divided by A2 B2 minus A3 B3 times lambda plus A1 B2 minus A3 B1 into A2 B1 minus A1 B3 divided by A2 B2 minus A3 B3 equal to 0. Now, one thing you need to notice that this equilibrium point, they represents the density or the number of species. Let us say it is a density, and it has to be positive, and hence for this to be positive, this has to be greater than 0, this has to be greater than 0. Similarly, this has to be greater than 0, this has to be greater than 0. So, for the existence of x star y star, where x star is not equal to 0 and y star is not equal to 0, both x star has to be positive and y star has to be positive, and condition for that is the numerator and the denominator has to be positive. Previously, we have something like A1 by A2 comma 0, both A1 and A2 are positive. So, this is obvious that this is a positive quantity, but here we have to follow the condition that A1 B2 minus A3 B1 must be positive, A2 B2 minus A3 B3 must be positive, and A2 B1 minus A1 B3 has to be positive. Now, when you look into the characteristic equation, the Routh-Hurwitz criteria gives you that if it is lambda square plus some coefficient, say d1 times lambda plus d2 equal to 0, then the system will be stable if d1 and d2 are both positive. There is another version, you can write it as lambda square minus of minus d1 into lambda plus d2. So, this represents the sum of the roots, this represents the product of the roots. So, we know the system is stable if both the roots, if real, their sum, both the roots if real, they has to be negative, and if they are negative, their sum will be negative and their product will be positive. So, this part has to be less than 0, this part has to be greater than 0. Already there is a minus d1 here, so it is less than 0. Now, if you want this to be positive, that is in this particular case, so you take this minus sign out, this becomes positive. So, in that particular case, this has to be positive. So, there are two ways of representing the equation. You just remember one way, otherwise sometimes it can be confusing. Say let us remember this only, lambda square plus d1 times lambda plus d2. So, both the signs has to be positive, and that will make d1 and d2 will be positive, that is the condition. Now, if we look into this particular thing, the product of the roots, we see that this is greater than 0 from here, this is greater than 0 from here, and this is greater than 0 from here. So, the existence of the equilibrium point makes that this particular expression is positive. So, it satisfies d2 greater than 0 automatically. Now, come to this particular expression, say this particular expression. The denominator is positive because of this condition. Now, if I want the numerator to be positive, so that d1 greater than 0 is satisfied, so my condition should be that a2 times a1 plus b1 into b2 minus a1 b2 b3 minus b1 a2 a3, this should be greater than 0. So, this is the condition that the non-zero equilibrium point x star y star will be stable if this particular condition is satisfied. So, when you do the numerical solution, when you choose your AIs and BIs, you have to be careful that this particular condition is satisfied, only then you get the system to be stable. Now, so much about the theory, let us look into the numerical solutions. Okay. So, we have, this is for species A. So, this is species A or species 1, and this is species 2. So, I will not go for 0 0 because I know that this is unstable. So, I choose the values in such a manner that I get this particular curves. Now, what does this say? This is for the species 1 and this is for the species 2. So, for a1 by a2 comma 0. So, this is the case where your species 2 goes to 0, that is extension, and your species 1 approaches this equilibrium point. Now, when this is going to approach this equilibrium point, we have already shown that B1 must be less than A1 B3 by A2. Now, if I pluck the values from here, A1 B3 A2, I will see that this value is coming to be 0.4. and B1 has to be less than 0.4. So, B1 is 0.2, which is less than 0.4, and hence the condition for stability has been satisfied. The numerical values are chosen in that manner. So, in this particular case, your species 1 survives and your species 2 goes to extinct. Both of them start with the same initial condition, that is 10. So, we have taken that x0 is equal to 10 and y0 equal to 10. So, x0 means the value of x at time t equal to 0. And starting with the same density or the same number of population, we find that in this particular case the species 1 survives and the species 2 goes to extinction. Maybe they do not get enough food or sunlight or space, and hence they cannot survive, they dies. The second example is where your species 1 they goes to extinct and your species 2 they survives. So, I have to change this particular set a little, and in this particular case you have 0 B1 by B2. So, your species 2 goes to this equilibrium point B1 by B2 and your species 1 goes to 0. and the condition for that is A1 must be less than A3 B1 divided by B2. So, here is your A3, here is your B1, here is your B2. If you substitute those values, you will get that this value is 0.3 and the value of A1 is 0.1, which is definitely less than 0.3, and hence we have a stability. So, since the system is stable, again you have started from the same equilibrium point 0, 0, and you see that your species 1 did not survive, whereas your species 2 survives. Our third example is where both of them survives. So, we have already checked the stability condition that we have derived, and using this particular numerical values, we find that this is the curve which they are giving. Now, what does that mean? It means that yes, both of them survives, both of them coexisting, but species 1 dominates over species 2. And why it dominates? Because somehow it managed to get more of the resources than species 2, and hence its growth is much more than this particular species. So, this curve is greater, I mean gives the greater value than this particular curve. The final example is, again I have taken a different set. So, what you see here is, this is species 1 and this is species 2. Both started with the same value 10. So, initially species 1 was dominating over species 2 till this point, and then the species 2 takes over and it now dominates species 1. So, this is an interesting example, and like this you can change your numerical set of values for AIs and BIs and get different kind of results. So, that comes to an end of the two species competition model. In our next lecture, we will be learning about the arms race model. Till then, bye bye.